Hi, I'm Mark von Drasik, and I just wanted to demonstrate pretty briefly a typical Ohm's law experiment that many of us do if we get to electricity, whether it's a first-year class or a second or an AP class. What's nice about these, for basic circuits, it's a pretty clean experiment. Typically, you get some pretty clean data, which you'll see in a few minutes. A very basic setup, which is appropriate when you're starting off any kind of electronics. The students don't typically have much experience with this. Most probably have never seen multimeters, if you have those. Perhaps they saw an electrician come into the house one day with those. In this case, I have an old analog ammeter connected to a breadboard, which most students probably haven't seen. A little wire jumper, some cabling, a power supply, and then some actual resistors here that you can plug into the breadboard. So students probably would understand pretty quickly what a complete circuit means, and once they have a visual in front of them, and they can start playing with it. So the idea here of this particular lab is to try and get students to do a lab first. To not have it just as a confirmation of things that you've already taught, but do it up front before you say a word about what Ohm's law is. Just by doing that, we're satisfying a bunch of bullet points within next generation science standards. Having students do the process of science, discovering things on their own, and then trying to confirm it with the textbook, perhaps. So in this case, there's really nothing more that we can vary on here besides changing the voltage with the power supply, changing the resistance, and seeing how that affects the primary quantity within electricity, of course, is electric current. So in the first experiment, the students can select whatever fixed resistance they want on their breadboard. Or if you have just like a little resistor board or something that's pre-made, whatever it is that you have, make sure that they have a fixed resistor for this first experiment. And then we're simply trying to find out, by varying the voltage, what kind of current do you get from that combination. Okay, so with my multimeter, I have it set up as a voltmeter. I'm going to touch the two little jumpers here that come into the bus lines, so the breadboard. And I can start to increase the voltage. And I'm starting to draw some current over here. I'll take it up to 100 milliamps in this case. Okay, so about 2.5 volts is producing 100 milliamps. And this is with a resistance of about 30 ohms. Okay, and so they can record that. One thing I try to get my students in the habit of doing is to do a wide range of values. Now in this case, the ammeter goes from 0 up to about 500 milliamps, or half an amp. And so I might tell them, in order to make a graph, you might want 4 or 5 different points so you can get a fit. They might just want to adjust it until they get to 100, now 200 milliamps. Okay, it goes up to about 5.3 volts in this case. Go up to 300, 400, 500, but do the full range that your equipment allows. As you'll see in a few minutes, that allows you to have a nice graph and to get more reliable fits that way. Okay, so it goes pretty quickly. You can get those data pretty quickly. Then comes the second experiment, where you'll want them to set the voltage to a fixed value each time they do this, but then vary how much resistance they have on the breadboard. And that, presumably you would have gone through series and parallel resistors before you get to the actual currents. It gives them good practice to play with the 3, 4, 5 resistors and get maybe 4 or 5 different resistance values. One thing they'll have to be careful of is each time they change things on the breadboard or a circuit board or on a resistor board is to turn down the power, get into those good safety habits, then change your circuit around. Then you can go back, remeasure, make sure you get back up to that same voltage, and record what effect that new resistance has on your current. Okay, so again, this is definitely a one-period lab. The students will get the hang of this pretty quickly. They can get their data. And we'll now go ahead and take a close-up, more of a close-up, on what the data looks like and what those graphs might look like and what the fits look like in order to get an end result, which hopefully turns out to be very close to what the textbook says is Ohm's law. Okay, so taking a look at the data that we would have collected from the experiment here for Ohm's law. Here I have the raw data, and this is the case where I had a fixed resistor and varied the voltage to see what effect voltage has on the current being produced in the circuit. Second set is the case where we had a fixed voltage each time, and then we saw the effect of changing the resistance of the circuit and how that affects the current. And so I have the two plots here. And it'll become very apparent, at least it should, this is a very clean experiment typically, that for the voltage on one end and you have the current here on the x-axis, however you set it up, you should get a nice linear fit. It should be apparent by eye, and certainly when you use Excel and start finding the best fit function, the linear fit is very, very close to 1. Nice and clean. And so it becomes obvious that current is directly proportional and linearly proportional to the voltage being applied to the circuit. The other one, though, some students might not be too used to seeing inverse relationships with data and nonlinear relationships with data. But if the data is pretty clean, it is inverse, it is nonlinear. In this case, again, we have the current on the y-axis and this is the resistance on the x-axis. Going through the different fits, the one that turns out to be the best fit function is actually a power law. And you won't be able to see it on the screen here, but this tells us that the current is proportional to resistance to the minus 0.865 power. Okay, so if you want to play the rounding off game, you know, minus 0.9, minus 1, thereabouts, it's just almost a perfect inverse relationship there. So current is proportional to about 1 over the resistance. Okay, so what do you do with this? So here's a case where a particular quantity, the current that we're thinking about, is proportional to two different things. And there's really nothing else that we could vary, so nothing else that we can measure in this experiment. And so what you want the students to be thinking in terms of is taking these two results individually and just kind of slapping them together. And now you can say that the current is proportional to voltage over resistance. And that's all there is. In this case, we won't worry about proportionality constants. They will have discovered Ohm's law. And if your students are anything like mine in the first year class, they have very little experience. The vast majority won't know much of anything about electricity. So Ohm's law will actually be new to them. And they can understand where it's coming from, where that relationship comes from. You're using computational thinking skills in this. We're using technology to plot data, to do fits, to find best fit functions, putting multiple results together. We're even using some technology. I would consider digital multimeters to be technology in order to collect those data. So there's one fairly simple experiment that you can do certainly within one class period. You know, you nail a lot of those bullet points within next generation science standards by using these computational thinking skills. So I hope this helps. This is going to be time for you to have a chance to work with your group. You know, get your own data, go through what the students would do, anticipate questions and problems and issues that the students are going to have. Think about the analysis questions that are in your copy of this lab. Are those appropriate for your students and what you want to get across? Feel free to modify those to fit your classes and how you plan on presenting something like this. And you know, enjoy it, and you know, just by reversing the way we do labs, by doing the lab first, letting the students discover what's going on, you know, have those discussions before you, the teacher, speaks about it, and suddenly we can start working in these next generation science standards and getting students doing the process of science. So I hope this helps a lot, and good luck with it.